80 times 10 to the power minus 6 meter cube. So we have our QZ already. So from here, we can directly put in our values. So shear XY at point A will be equal to V, which is 90 times 10 to the power 3, multiplied by 80 times 10 to the power minus 6, divide by the second moment of area, 5.8133, times 10 to the power minus 6. Thickness now is 0. No, now the thickness have to be careful. Okay. So the thickness now, right, this is point A, like what we see earlier. The thickness is twice multiplied by 0.02. You will not want to use the 0.16 because that will give you a shear stress that is lower in value, right? No points calculating a shear stress that's lower in value, where the higher value will actually induce failure. Okay, for that reason. Y2 over here, because you have left and right webs. Okay, so this will be equal to 90 power 3 times by 80 power minus 6 divided by 5.8133 power minus 6 divided by 2 divided by 0.02 is equal to 30.963 times 10 to the power 6 Pascal. Okay. So this is straightforward. Next, we're going to find point B. Okay, we're going to find point B. I don't see anyone, any question, or you're all okay? I hope if you have any question, please ask me, okay? Regarding this example. Okay. So now we're going to find shear XY. At point B now. Okay, so I'm going to sketch where the centroid is, geometric global centroid. Okay, so this is where. And we know that the height from here, not the height, but we know that the distance from here to here is 35 millimeters. Okay, we know that. Okay. So again, the formula we're going to apply very straightforward, nothing to panic about. Whether is it point A or point B, we know that Vy is constant. We know that Izz is constant. We only need to find what is our Qz and T. So T we know over here is T is equal to twice left and right, and the thickness is equal to 0.02. So this is equal to 0.04 meters. Okay. So the next one we have to find is our QZ. So the area of interest now, okay, is this area over here and this area over here. Why I draw that? Remember, I told you guys the function, the y variable. Okay, if I'm going to draw a straight line like this, right, at cross point B, right. Remember what I told you? This line is our what? Constant what? Shear stress line. Right? That is our constant shear. And it happened to intersect both areas, right? Left and right web. So when that's the case, so you have to find what is your QZ. So this will be equal to width, depth, y bar. Okay. So the width be twice multiplied by the width 0.02. The depth is equal to 0.03. Then the y bar. So we know that the distance from to here is 100 minus 35, which is equal to 65. Okay, so this will be equal to, oh, I do apologize, let's work in millimeters. So 2 times 20 multiplied by 30. I'm not writing my 30 properly. Multiplied by 30. And then you have 65 minus by 30 divided by 2. Okay, because if this is the y bar, this is our y bar, right? We know that the distance from here to here is what? Oh, I got that one already. The distance from here to here, 65. The distance from here to here, this is 30 divided by 2. So over here up to here, that is our y bar. So this will be equal to 65 minus 30 divided by 2 times by 30 times by 20 times by 2 is equal to 60 times 10 to the power 3 millimeter cube, or 60 times 10 to the power minus 6 meter cube. Okay, so from this case, you can determine the shear xy at point B will be equal to 90 times 10 to the power 3 divided by 5.81 5.8133 times 10 to the power minus 6. And then we know our QZ is 60 times 10 to the power minus 6. And then we know our thickness, which is equal to 0.04. So when we work this out, 90 power 3 times 5, 90 power 3 times 5.8133 power minus 6. 90 power 3 times 60 power minus 60 power 5.8133 power minus 60 power 0.04 is equal to 23.20. 23 point, I get 23, wait, 90 power 3 times 60 power minus 6 divided by 5.8133 power minus 6 divided by 0.04, 23.223. Okay, 23.223 times 10 to the power 6 Pascal. Now I'm going to do one more, okay, one more position, okay, before we derive the equation for the distributed. So what I'm going to do now is we are going to do a we are going to, so again, this is a centroid. We are now going to determine the shear xy at the centroid. Okay, so I'm going to use two ways of doing it, and the answer, if it's done correctly, the answer has to be the same. Okay, and there is an easier way and there's a more difficult way. Okay, so I will show you two methods. Okay, so the first method I'm going to consider, we are going to look at the top section, and the second method is we are going to look at the bottom section. And we are aware that this distance is 35 millimeters. Okay, so we are going to find the shear stress of the centroid. So if we were to look at the top section, right? So the top section, the QZ is equal to QZ of the flange plus by QZ of the web. As you already know by now, this is known as the flange. This part is known as the web. Okay, so I'm going to section this now. Okay, so we are going to look at QZ of the flange. Okay, so we're going to determine that value now. So that value, so again, the QZ is width, which is 160, depth, which is 20. The Y bar is equal to 35 minus by 20 divided by 2. Okay, so that is the flange. Okay, so let me check again. 35, 20 divided by 2, correct. Okay, then the web plus by twice. The width is 20. The depth, so now we know that this distance is equal to what? 15, right? So it's 15 multiplied by 15 divided by 2. Okay, that is the Y bar. So this will be equal to 35 minus 20 divided by 2 times by 20 times 160 is equal to 80 times 10 to the power 3 plus 1125 with 20 times 15 times 15 divided by 2 times 2 2 times 20 times 15 times 15 divided by 2 is equal to 4500 or 4.5 times 10 to the power 3 . So this will be 80 power 3 plus 4.5 power 3 is equal to 84.5 times 10 to the power 3 millimeter cube, or 84.5 times 10 times 10 to the power minus 6 meter cube. Okay, so from here, your shear XY at the centroid will be equal to Vy, which is 90 times 10 to the power 3 divided by 5.8133 times 10 to the power minus 6 multiplied by 84.5 times by 10 to the power minus 6, and then you divide by 0 or twice of 0.02 because it's left and right. Okay, so 90 power 3 times by 84.5 power minus 6 divided by 5.8133 power minus 6 divided by 2.002 is equal to 32.705. Okay, so 32.705 times 10 to the power 6 Pascal. Now, if we were to just consider the bottom section, okay, because the first moment of area cannot cross the centroid, yes or no? Right? So if you take the bottom section, right? If we look at the bottom section, so the bottom section, the area we're going to consider is these two areas over here. I'm shading now. Okay. So we know that. So this is for bottom section. This is by considering the top section. So QZ is equal to QZ of the web. So the width, so you have left and right web. The width is 0.02, right? The thickness is equal, let's do it in millimeters, okay? So it's 20. And we know that the distance from here to here is 65 depth. The Y bar is 65 divided by 2. So 65 times 65, 20, and it's equal to 84.5 times 10 to the power 3 millimeter cube, or 84.5 times 10 to the power minus 6 meter cube. And you happen to see that the area, first mode of area, whether you take from the bottom section to the centroid or the top section, is the same. But if you look at the working, it's so much easier to do the what? to do the bottom section. You make less what? You will make less mistake. Okay, you make less mistake on